You hear it everywhere. Quantum computers. The news whispers of their power. Governments are pouring billions into their development. The world is buzzing with talk of quantum computing. Once tucked away in theory, it's now bursting into the mainstream. Breakthroughs and bold claims are making the whispers louder. Quantum computing could reshape how we understand reality itself. Headlines scream about quantum computers breaking the internet and launching a new tech era. It's enough to make your head spin. Are we on the brink of a utopia or a quantum-powered dystopia? The hype is intense but not always accurate. We need to sort out what's real and what's just noise. Beneath the buzz, there's real potential. Quantum computing could transform industries, from medicine to AI. But first, let's understand what makes it so powerful. Just imagine a world where diseases like cancer and Alzheimer's are wiped out, thanks to quantum simulations that crack the mysteries of protein folding and drug development. Or picture a future where we tackle climate change head-on, using quantum algorithms to optimize energy systems and design breakthrough carbon capture technologies. That's the promise of quantum computing, a world transformed by our ability to tap into the weirdness of the quantum realm. It's a future where the limits of classical computing just don't apply anymore and the impossible starts to feel, well, possible. But this journey into the quantum world, it starts with understanding the basics. We need to look at how classical computing, the kind we use every day, differs from the strange and fascinating world of quantum mechanics. Only by understanding those differences can we really appreciate just how revolutionary quantum computing might be. So yeah, buckle up. We're about to take a deep dive into the strange and wonderful world of quantum computing. Our digital world, everything from the phones in our pockets to the vast internet that connects us, is built on a foundation of ones and zeros. These are bits, the basic units of information in classical computing. Like a light switch that's either on or off, a bit can only be in one of two states, 0 or 1. Picture a massive sea of light switches, each one representing a bit. By flipping these switches in specific patterns, we can represent anything. Letters, numbers, images, videos, even the complex instructions that make up the software we use every day. These bits are handled by transistors, which are like microscopic traffic controllers. They guide the flow of electricity, making sure information moves where it's supposed to, based on the rules of a program. Basically, classical computers do their magic by manipulating bits through logic gates to perform tasks and solve problems. It's a system that's incredibly powerful, and it's changed our world in countless ways. But even with all its strength, classical computing has its limits. It's still bound by the binary nature of bits and the rules of classical physics. Logic gates are, well, the workhorses of classical computing. Really, the fundamental building blocks of all digital circuits. They take one or more bits as input and produce a single bit as output, based on a specific logical operation. You can think of them as simple decision makers, evaluating conditions and giving us a predictable outcome. One of the simplest logic gates is the AND gate. It takes two bits as input and outputs a 1 only if both input bits are 1. Otherwise, it outputs a 0. Another fundamental gate is the NOT gate, which just flips the input bit. If the input is 0, the output is 1, and vice versa. Now, by combining these simple logic gates in more and more intricate arrangements, we're able to create complex circuits that can perform some incredibly sophisticated computations. From basic arithmetic to intricate algorithms, everything our computers do, at the most fundamental level, boils down to the orchestrated manipulation of bits by these logic gates. The real power of classical computing comes from the sheer number of transistors we can pack in and the complexity of the circuits we're able to build. But as we continue pushing the limits of miniaturization, we're also approaching a fundamental physical barrier. For decades, Moore's law has held true. The number of transistors we can fit on a chip has doubled about every 2 years, giving us exponential increases in computing power. But honestly, this remarkable trend can't go on forever. We're getting close to the physical limits of how small we can make these components. Transistors are now so tiny that they're approaching the size of atoms. And at these scales, the weird laws of quantum mechanics start to take over, and the classical rules that usually govern transistor behavior begin to break down. Electrons, the little guys that carry electrical current, can start to tunnel through barriers, which leads to unpredictable behavior. On top of that, heat dissipation becomes a serious issue. We're reaching a point where making transistors any smaller isn't just hard, it's fundamentally impossible using classical methods. This looming end to Moore's law has kicked off a global search for alternative computing paradigms. And right at the forefront of this search is the fascinating and honestly mind-bending world of quantum computing. The limitations of classical computing really start to show when we're faced with certain types of problems. Things like simulating complex molecules, optimizing massive logistics networks, or even breaking modern encryption. These tasks demand computational power that far exceeds even our most powerful supercomputers. For these kinds of problems, classical computers just hit a wall. Their binary bits and step-by-step processing simply can't keep up. It's kind of like trying to solve a million-piece jigsaw puzzle one piece at a time. It's technically possible, sure, but practically, it's just not feasible. This bottleneck has driven the search for brand new computing paradigms, technologies that can go beyond the limitations of classical bits and logic gates. Researchers are exploring all sorts of novel approaches, from neuromorphic computing that mimics the human brain, to DNA-based computing that taps into the power of biology. But among all these contenders, quantum computing stands out. It's by far the most radical and potentially transformative. It doesn't just promise marginal gains, it offers an exponential leap in computational power by leveraging the strange and counterintuitive laws of quantum mechanics. Quantum computing isn't just about speed, it's about rethinking what it means to compute. It taps into the strange laws of quantum mechanics where particles can exist in multiple states at once. At the core is the qubit, the quantum version of a bit. Unlike a regular bit, a qubit can be both 0 and 1 at the same time, like a coin spinning in midair. This superposition gives quantum computers their incredible power. Add entanglement, where qubits share the same fate across distances, and the possibilities grow even more. Together, these principles let quantum computers tackle problems classical ones simply can't. To understand the magic of quantum computing, we really need to venture into the strange and wonderful world of quantum mechanics. It's a realm where the rules of classical physics, the physics of our everyday experience, just break down, and a whole new set of rules, often counterintuitive and honestly kind of mind-boggling, take over. Imagine a world where particles can be in multiple places at once, where information can be teleported across vast distances, and where just observing something can actually change its state. This is the quantum realm, a place where our classical intuitions are constantly being challenged. For much of the 20th century, quantum mechanics stayed mostly in the realm of theoretical physics, just a set of equations used to explain the behavior of subatomic particles. But as our technology advanced, we gained the ability to actually manipulate and control these quantum phenomena, opening up a whole Pandora's box of possibilities. Quantum computing is a testament to our growing mastery over the quantum world. It represents a fundamental shift in how we think about computation, a real paradigm shift, one that harnesses the weirdness of quantum mechanics to perform calculations that were once thought to be totally inconceivable. So, at the heart of quantum computing lies the qubit, the quantum equivalent of the classical bit, but unlike its classical counterpart, which can only be either a 0 or a 1, a qubit can exist in a superposition, a state where it's both 0 and 1 at the same time. Imagine a coin spinning in the air. It's not heads, it's not tails, but it's kind of both until it lands. That's the essence of superposition. A qubit holds the potential for both 0 and 1, existing in this blurry, probabilistic state. This ability to inhabit multiple states simultaneously is exactly what gives quantum computers their immense potential power. It's like having a computer that can explore all possible solutions to a problem at the same time, rather than having to try each one sequentially. But the true power of qubits? It's really unleashed when we entangle them, linking them together in a way that classical physics just can't explain. Alright, so let's talk about superposition. It's really the secret sauce of quantum computing. It's the idea that a qubit can be in multiple states at once. Think of it like having a coin that doesn't just land on heads or tails but somehow, both at the same time. Kinda wild, right? This both-at-once capability is what lets quantum computers explore a huge number of possibilities all at once. Now picture trying to find your way through a maze. A regular classical computer would need to try each path one by one until it eventually finds the exit. But a quantum computer? It could explore all the paths at the same time, which, yeah, dramatically speeds things up. This kind of parallelism is what gives quantum computers the ability to tackle problems that might take classical computers, say, billions of years to solve. It's like having a gigantic parallel processor, but instead of millions of processors, you're tapping into the power of quantum superposition. And here's the thing. Superposition is just the beginning. Once you start combining it with entanglement, well, that's when the really mind-bending stuff starts to happen. So now let's dive into entanglement, which, by the way, Einstein famously called spooky action at a distance. It's kind of like a telepathic connection between qubits. When two qubits are entangled, they're linked in such a way that they actually share the same fate, even if they're separated by, like, massive distances. Imagine two coins flipping in perfect sync, one in New York and the other in Tokyo. That's basically what entanglement is. If you measure the state of one entangled qubit, you instantly know the state of the other, no matter how far apart they are. This kind of interconnectedness is what lets quantum computers perform calculations in ways that classical computers just can't. It's like you've got this network of processors that can communicate instantly, no matter where they are. Entanglement is really the key to unlocking the full potential of quantum computing. It enables us to tackle problems that even the most powerful classical supercomputers just can't handle. Alright, so just like classical computers use logic gates to manipulate bits, quantum computers use quantum gates to manipulate qubits. But here's the twist. These gates operate on the bizarre principles of quantum mechanics, which means they can do things that classical gates simply can't. Instead of just flipping bits from 0 to 1, quantum gates can rotate qubits, changing the probability that they'll collapse into a particular state. And they can also entangle qubits, creating these strange correlations that go way beyond anything classical logic can explain. Now, designing and implementing these quantum gates? Yeah, it's no walk in the park. It requires super precise control over the quantum states of individual atoms or photons, and you've got to shield them from environmental noise that could mess with their delicate superposition. In the end, the real art of quantum computing is choreographing this intricate dance of qubits through a sequence of quantum gates. It's like conducting a symphony made of entanglement and superposition, all leading to the final result of the computation. Building a quantum computer isn't just about shrinking existing tech, it's about inventing a whole new kind of machine governed by quantum mechanics. Qubits are fragile, easily disturbed by noise, and must be kept colder than outer space to maintain their quantum state. From superconducting circuits to trapped ions and photons, each approach has its own strengths, but all face the same challenge: scaling up while keeping errors down. Classical computers explore one solution at a time. Quantum computers explore many at once thanks to superposition and entanglement. This parallelism could give quantum machines an exponential edge in solving certain problems. Imagine searching for a grain of sand on every beach. Classical computers go grain by grain. Quantum computers? They scan them all at once. That's why scientists and entrepreneurs are racing to unlock quantum computing's full potential. Simulating molecules is incredibly hard for classical computers, but quantum computers speak nature's language. Their qubits can model quantum interactions directly, enabling breakthroughs in materials science and drug discovery. From zero-resistance superconductors to precision-targeted medicines, quantum simulations could revolutionize how we design the world around us. Optimizing complex systems like traffic, supply chains, or financial portfolios is tough for classical machines. Quantum algorithms can explore countless possibilities at once, offering faster, smarter solutions. From reducing emissions to predicting market shifts, quantum computing could reshape how we manage complexity. AI is transforming our world, but training powerful models demands massive computing power. Quantum machine learning could accelerate this process, enabling AI to detect diseases earlier, understand language better, and discover drugs faster. By merging quantum computing with AI, we may unlock the next wave of intelligent systems. Today's encryption protects everything from bank accounts to private messages, but quantum computers could break it. Algorithms like Shor's could crack codes once thought unbreakable, prompting a global push for quantum-resistant cryptography. The race is on to secure our digital world before quantum computers reach full power. Quantum computing is where classical computing was decades ago. Early, clunky, but full of promise. Governments and companies are investing heavily, and the pace of progress is accelerating. This isn't just about faster machines, it's about rethinking how we solve the world's hardest problems. The quantum revolution is underway, and its impact could be profound. Tech giants like Google, IBM, and D-Wave are leading the charge in quantum computing. Google's quantum AI team made headlines with claims of quantum supremacy. IBM is building a global quantum ecosystem offering cloud access to real quantum machines. D-Wave is taking a different path with quantum annealing, already delivering solutions to real-world problems. In 2019, Google's 53-qubit Sycamore processor completed a task in 200 seconds that would take a supercomputer 10,000 years. The task was tailored to quantum strengths, but it marked a major milestone. It proved that quantum machines can outperform classical ones, at least for specific problems. Google continues to refine its systems, pushing toward more practical applications. IBM isn't just building quantum hardware, they're building a whole ecosystem. Through the IBM Quantum Experience, users worldwide can access real quantum computers via the cloud. Their open-source platform, Qiskit, empowers developers to create and share quantum programs. With strong hardware and a global community, IBM is accelerating quantum innovation. D-Wave focuses on quantum annealing, a method ideal for optimization problems. Their systems are already in use, helping companies like Volkswagen improve traffic flow. While debate continues over their performance, D-Wave's practical applications are gaining attention. Their unique approach adds valuable diversity to the quantum landscape. Beyond the tech giants, startups are lighting up the quantum space with bold ideas and fresh talent. From topological qubits to quantum software platforms, these companies are tackling niche challenges with big potential. Their innovation and competition are speeding up the race toward practical quantum computing. Quantum computing has sparked excitement and skepticism. Some doubt we'll ever overcome the technical hurdles or that current algorithms offer real advantages. But like the early days of classical computing, progress takes time. The journey is tough, but the potential rewards make it worth the effort. Google's quantum supremacy was a landmark, but not the endgame. The task was narrow, and practical quantum advantage is still ahead. Supremacy is a spectrum, not a single moment. Each breakthrough brings us closer to solving real-world problems with quantum power. The specter of quantum computers breaking the encryption that protects our digital lives Yeah, that's been looming pretty large in recent years. The thing is, certain quantum algorithms, like Shor's algorithm, can factor large numbers exponentially faster than any classical algorithm we know. And that poses a serious potential threat to the encryption methods we rely on today. That said, it's really important to remember that this threat isn't immediate. Building quantum computers powerful enough to break current encryption standards is still a massive challenge. We're talking years, maybe even decades, of further development before that becomes a reality. And here's the good news: the cybersecurity community isn't just sitting around. Researchers are actively working on quantum-resistant cryptography. These are new encryption methods that are believed to be secure, even against attacks from quantum computers. So yeah, the race is definitely on. The goal is to roll out these quantum-resistant encryption methods before quantum computers reach that level of power. That way, we can make sure our digital lives remain secure and private, even in the quantum era. So the journey towards practical quantum computing is, well, paved with some pretty formidable challenges. Building and controlling these delicate quantum systems, yeah, it's a monumental engineering feat that really pushes the boundaries of our technological capabilities. One of the biggest hurdles we face is maintaining qubit coherence. That's the fragile state of superposition that gives quantum computing its unique power. But qubits? They're incredibly sensitive to noise and errors. I mean, even the tiniest environmental disturbance can throw them off. Another major challenge is scalability. Creating quantum computers with thousands or even millions of qubits, which will need to solve complex, real-world problems, is honestly a daunting task. Right now, quantum computers are still relatively small. Scaling them up while keeping qubit coherence and managing errors, yeah, that's a huge engineering challenge. And then there's the software side of things, developing new quantum algorithms. These are the tools that let us actually tap into the power of quantum computers. We've made some progress, sure, but we're still quite far from unlocking their full potential for solving a broad range of practical problems. Predicting the future of quantum computing? Well, it's kind of like looking into a crystal ball. The field is evolving so fast with new breakthroughs and, yeah, unexpected challenges popping up all the time. What feels like science fiction today could totally become reality tomorrow. And honestly, we might see applications we haven't even dreamed of yet as the tech matures. But here's what we do know. Quantum computing has the potential to be just as transformative as the invention of the transistor or even the internet. It could revolutionize medicine, speed up scientific discovery, reshape entire industries, and really push the boundaries of what's computationally possible. As we go deeper into the quantum realm, we've got to move forward with both excitement and, well, a bit of caution. The ethical implications of such a powerful technology really need thoughtful consideration, and we have to make sure its benefits are shared fairly and equitably. The quantum future, it's uncertain, yeah, full of both promise and peril. But if we stay curious, work together, and navigate the unknown with wisdom and foresight, we can use quantum computing to build a brighter, more sustainable future for everyone. The air crackles with anticipation. Quantum computing, once a whisper in theoretical physics, now dominates headlines and fuels both awe and skepticism. Is this the dawn of a new epoch or just another hype cycle? We've heard bold promises before: flying cars, the paperless office, fusion energy, but history shows that skeptics often miss the next big leap. Today, quantum computing teeters between inflated expectations and real world-changing potential. With billions invested and breakthroughs emerging, the question remains: hype or history in the making? Predicting the future is a fool's errand, especially in a field as dynamic and rapidly evolving as quantum computing. But if the past few years are any indication, the next decade promises to be a period of extraordinary progress, marked by breakthroughs that could shift the technological landscape in profound ways. While the prospect of fully fault-tolerant universal quantum computers that can solve any computational problem with unimaginable speed might still be decades away, we're likely to see the emergence of quantum advantage in specific domains much sooner. Imagine quantum simulations that unlock the secrets of new materials, leading to superconductors that revolutionize energy transmission, batteries with unprecedented capacity, and catalysts that accelerate drug discovery. Picture quantum algorithms that crack the optimization problems plaguing logistics and finance, leading to more efficient supply chains, reduced waste, and financial models that can better predict and mitigate market volatility. Envision quantum-enhanced machine learning algorithms that can analyze complex datasets with unprecedented speed and accuracy, accelerating breakthroughs in healthcare, personalized medicine, and materials science. These are not pipe dreams, but tangible possibilities, driven by the relentless pace of innovation and the convergence of brilliant minds across disciplines. Physicists, computer scientists, engineers, mathematicians, and entrepreneurs, all united by a shared belief in the transformative power of quantum computing. The quantum revolution, unlike previous technological upheavals, will not be televised. It's happening quietly, in laboratories and research centers around the world, driven by the insatiable curiosity of scientists, the ambition of entrepreneurs, and the strategic calculations of governments. This is not a spectator sport. Understanding the implications of quantum computing, separating the hype from the reality, and preparing for its impact, requires more than passive observation. It demands a renewed sense of curiosity, a willingness to engage with complex concepts, and a commitment to fostering dialogue between experts and the public. We must resist the temptation to relegate quantum computing to the realm of the esoteric, the exclusive domain of physicists and mathematicians. Just as the internet, once the playground of academics and tech enthusiasts, permeated every aspect of our lives, quantum computing, in its own time and way, will touch countless industries, professions, and aspects of human endeavor. This is a call to action for students to explore the mind-bending world of quantum mechanics, for educators to incorporate quantum concepts into their curricula, for business leaders to envision how this technology might disrupt their industries, and for policymakers to grapple with the ethical and societal implications of this powerful new tool. The quantum revolution is not merely a technological shift, it's a cultural one, demanding a fundamental reorientation in how we think about computation, information, and even reality itself. It challenges our deeply ingrained intuitions about the world, inviting us to embrace the counterintuitive and the paradoxical. In a world increasingly defined by complexity and interconnectedness, quantum computing offers a glimmer of hope, a tool for navigating the challenges of the 21st century, from climate change and resource scarcity to pandemics and cybersecurity threats. But like any powerful tool, it's a double-edged sword, capable of being used for good or ill. The future of quantum computing is not predetermined. It's being written right now through the collective choices we make, the research we fund, the ethical frameworks we establish, and the conversations we have. It's a future we will inherit together, shaped by our shared hopes, fears, and aspirations. The quantum revolution, like all revolutions, is an invitation to embrace the unknown, to challenge our assumptions, to collaborate across disciplines and cultures, and to shape a future where this powerful new technology empowers us to address humanity's greatest challenges and unlock a future brimming with possibilities.